So today, I'm going to explain why time dilation occurs. Time dilation is a product of special relativity, which is based on two ideas. First, physics are identical in all inertial, or constant speed, reference frames. I.e., if you were to throw a ball on a cruising airplane, it would behave exactly the same as if you were to throw it on the ground. So there is no absolute reference frame. Velocities are all relative to each other. I discussed this concept a little in my invariant light speed video. In that video, I explained why we know light speed is constant, which is the second idea special relativity is based on. So, while the speed of the ball you threw on the airplane may vary, depending on whether you measure it on the ground or on the plane, everyone measures light as going the same speed. It is a constant 299,792,458 meters per second. From this, we can see that time is in fact not constant, as is normally assumed. Special relativity also shows that, when moving at different velocities, mass is relative, length contracts, and simultaneous events for one person are not simultaneous for everyone. It also gave rise to the well-known E equals mc squared. However, I will not look into any of those here. This video will focus solely on time dilation. To prove this, let me introduce a special kind of clock. This clock has a light source on the bottom and a sensor at the top. The clock emits a beam of light which travels a distance d and hits the sensor. We can calculate how much time has passed by dividing the distance traveled by the speed of light, c. Now let's say we put this clock on a train. From the perspective of the person on the train, the light simply goes up and down. The time t sub t elapsed for one tick of the clock is d divided by c. However, from the perspective of a person on a nearby platform, it appears as if the light moves at an angle, due to the added velocity, v, of the train. So the path of the light looks something like this. From what we know about triangles, this distance, the hypotenuse, is longer than this distance. So, from the perspective of the person on the platform, the light has to travel a farther distance. Since light has to move at a constant speed, the only possible conclusion is that, from the perspective of the person on the platform, time is slower for the people on the train. We can see this mathematically. In a time, t sub p, measured by the platform person, the train moves a distance v times t sub b, and the light moves a distance c times t sub b. The vertical distance between the source and the sensor is d. We can relate these distances through Pythagorean's theorem. Through a bit of rearranging, we see that t sub p squared times c squared minus t sub p squared times v squared equals d squared. Factoring out a t sub p squared, and dividing both sides by c minus v squared, as well as taking the square root, we see that t sub p equals d over the square root of c squared minus v squared. This is how much time has elapsed on the train from the platform person's perspective. We can take this one step further and see, mathematically, how much dilated time is for the people on the train from an outsider perspective. Because the train was not moving up and down, only left to right, the vertical distance is the same for both observers, on and off the train. Plugging in a rearranged form of the time measured by the train observer, we see that t sub p equals t sub t times c divided by the square root of c squared minus v squared. Multiplying the top and bottom by 1 over c, and distributing the 1 over c into the square root, we see that t sub p equals t sub t divided by the square root of 1 minus v squared divided by c squared. As such, time on the train passes 1 over the square root of 1 minus v squared divided by c squared times slower than it does on the platform from the perspective of the people on the platform. Another source of time dilation comes from general relativity. General relativity is like special relativity, except it deals with non-inertial, or accelerating, reference frames. Just as physics behaves the same for inertial reference frames, there is no difference in the way physics behaves for something under constant acceleration, but without gravity, and for something only under the effect of gravity. I.e., if you were in a spaceship accelerating at a constant 9.8 meters per second squared, and you threw a ball, it would behave exactly the same as on Earth. From this, it was determined that gravity is caused by objects with mass distorting spacetime. To get an idea of what this is like, imagine spacetime being a large bedsheet that is stretched taut. Now imagine putting a basketball, representing, say, a planet, on the sheet. The sheet bends down towards the ball, creating a curvature such that if you were to put a marble on the sheet, it would roll towards the ball. Likewise, a planet distorting spacetime will draw things toward it because the objects will just follow the curve of spacetime. This is how gravity actually works. Going back to the sheet example, you may also notice that the basketball stretches out the sheet as you get closer to the ball. The same thing is true for real life. Any object with mass stretches spacetime when said object curves spacetime. This stretching literally lengthens space and time, so time is longer where there is more gravity. Admittedly, any of these time dilation effects are negligible for any situation a human will be in, at least anytime soon, but they still occur. Nevertheless, hope you enjoyed it, hope you learned something, and see ya!